say you're sorry. How would I know? Why should I care? Please don't bother trying to find her. She's not there.
In the first part of this lecture, we'll discuss existence and uniqueness for finite fields. So what are we going to prove? We'll prove that for every prime p and every positive integer n, there is a finite field of order p to the n. And then we'll prove that this finite field is unique up to isomorphism. That is, if you have any finite field of order p to the n, it is isomorphic to this finite field of order p to the n that we're going to construct. And once we prove that this is true, then we can give a name to this unique up to isomorphism field of order p to the n. We'll call it f sub p to the n. And the big idea here is going to be that we're going to construct this field as the splitting field of a certain polynomial over f of x. And then we're going to use what we know about uniqueness of splitting fields up to isomorphism to prove this uniqueness of this finite field up to isomorphism. Okay, so the idea is going to be to construct this field as the splitting field of a certain polynomial. So if you remember what this polynomial is, this will take you a long way towards remembering the whole argument. So let's let f of x be x to the p to the n minus x, a polynomial in fp bracket x. What kind of polynomial is it? This is a separable polynomial. Why? You take the derivative, you get this p to the n comes down, but p to the n is 0 in fp. So you get a 0 here and then a minus 1. So the derivative is minus 1. So f of x is certainly relatively prime to its derivative. So what does it mean that it's separable? It means that in a splitting field for f of x over fp, f of x has p to the n distinct roots. All right, so we know that such a splitting field exists. Let's name it. Let's say that L is a splitting field for f of x over fp. Okay, so now we're in a situation where we have these p to the n special elements in L. They are the roots of this polynomial. And that is where our finite field is going to come from. Okay, so this is the big idea to remember. So what do I mean more precisely? We're going to show that the set of roots of this polynomial in a splitting field is a finite field of order p to the n. So let's take two of these roots. So alpha and beta are going to be elements in L that are roots of f of x. So what does that mean? Alpha to the p to the n equals alpha, beta to the p to the n equals beta. And it's straightforward to show things like, what is alpha times beta to the p to the n? Well, it's alpha to the p to the n, which is alpha, times beta to the p to the n, which is beta. So this is alpha times beta. So the product of two of these roots also satisfies x to the p to the n equals x. What happens if you take the inverse of one of them? Well, you have alpha inverse to the p to the n. That is alpha to the p to the n inverse, which is alpha inverse. You can also show that if you take alpha plus beta to the p to the n, well, what is that? We know that in a ring of characteristic p, alpha plus beta to the p is alpha to the p plus beta to the p. And it's a straightforward exercise now to see that if you take alpha plus beta to the p to the n, what you get is alpha to the p to the n plus beta to the p to the n, which is alpha plus beta. So if this is not immediately clear, I encourage you to think about the case of n equals 2 and how alpha plus beta to the p squared, how to write that in terms of alpha plus beta to the p. There are more things you can check. I mean, if you instead take alpha minus beta to the p to the n, you'll see that you're also still get something that satisfies x to the p to the n equals x. So what are we seeing with all these relations is that if you let f be the set of p to the n distinct roots of f of x in L, f is a subfield of L. It's closed under addition, subtraction, inverses, multiplication, you name it. So we have this subfield of L of order p to the n, and it contains all of the roots of f of x. So what does that mean? F of x, well, we know it splits completely in L bracket x, but it already splits completely in this f bracket x. So what is L? It's a splitting field for f of x over fp. So part of the definition of a splitting field is no proper subfield of this splitting field that contains your base field fp. In no proper subfield does this polynomial already split completely. So what does that say? That's saying that f can't be a proper subfield of L because that would contradict L being a splitting field. So f is a splitting field for f of x over fp. F is equal to L. So it's this polynomial that already contains all of the roots of f of x in L, and L is the smallest extension of fp that contains all of those roots, so f equals L. But now what have we seen? F is a subfield of L, f is equal to L, and f has p to the n elements exactly. So f is a finite field of order p to the n. Another way to write this is just what is the dimension of f as a vector space over fp? Because it has p to the n elements, this dimension is n. So what have we seen? We've seen that for every prime p and every positive integer n, we can construct a finite field of order p to the n by taking the splitting field of the polynomial x to the p to the n minus x in fp bracket x. So that proves the first part of this theorem. I'm going to pause and erase, and we'll use the uniqueness of splitting fields up to isomorphism to prove the uniqueness of this finite field of order p to the n up to isomorphism. We now want to show the uniqueness part of this statement. That is, if we have any finite field of order p to the n, it's isomorphic to this finite field of order p to the n that we constructed as a splitting field for the polynomial x to the p to the n minus x over fp. So we're just going to start with a finite field of characteristic p. So we know that its prime subfield is fp, and it's a vector space over fp. And because it's finite, the dimension of that vector space is finite. So it's some positive integer n. So this finite field f is a vector space of dimension n over its prime subfield fp. So this dimension is n, which means that the number of elements in this field is p to the n. All right, so what do we know about this field f? One thing that we know is that the multiplicative group of a finite field is cyclic. So f star is cyclic of order p to the n minus 1. That means that alpha to the p to the n minus 1 equals 1 for any alpha in f star. So if you multiply both sides of this equation by alpha, then you get something that's true, not just in the case that alpha is in f star, but also for alpha equals 0. So alpha to the p to the n equals alpha holds for any alpha in f, not just in f star. So what does this mean? Alpha is a root of the polynomial x to the p to the n minus x for any of the p to the n elements alpha in this finite field f. So f is an extension of fp that contains all of the p to the n distinct roots of this polynomial. Any splitting field for this polynomial has to have at least these p to the n elements. So there's no way that a proper subfield of f already has the property that this polynomial splits completely into linear factors. So what are we seeing? F is a splitting field for x to the p to the n minus x over fp. Okay, so now we know that any finite field of order p to the n is a splitting field for this polynomial over fp, but splitting fields are unique up to isomorphism. So all of these splitting fields are isomorphic to each other. And that's the end of the proof. We've seen that any field of order p to the n is isomorphic because all of these, any splitting field for x to the p to the n minus x, that these are all isomorphic. So I'm going to pause and erase, and then we'll discuss how this construction here in terms of splitting fields is related to some of the earlier things that we have discussed about finite fields. we've proven that for each prime p and each positive integer n, there is a finite field of order p to the n by constructing it as the splitting field of a certain polynomial in fp bracket x. So we had talked about finite fields earlier, much earlier, when we talked about quotients of polynomial rings by ideals generated by irreducible polynomials. We had seen that if you take fp bracket x and you mod out by the ideal generated by p to the x, this is a finite field of order p to the n if p of x is irreducible of degree n. So what have we done? We've constructed this finite field of order p to the n as a splitting field of a certain polynomial. This looks different than constructing a field as the quotient of fp bracket x by the ideal generated by some polynomial. I mean, for one thing, we're not claiming that x to the p to the n minus x is an irreducible polynomial in fp bracket x. It isn't. So this feels different. So how does this relate to what we've been talking about? Well, if you look at finite fields this way, then if you want to prove the existence of a finite field of order p to the n, then all you need to do is say for each prime p and each positive integer n, there exists at least one irreducible polynomial p of x in fp bracket x of degree n. That would show that you could always construct a finite field of order p to the n as the quotient of fp bracket x by the ideal generated by some irreducible polynomial. Okay, now we know that there exists a finite field of order p to the n for each p and n. So did we prove that there's always at least one irreducible polynomial in fp bracket x of degree n? Not so clear, because it's not clear that every finite field of order p to the n can be written as, or is isomorphic to, fp bracket x mod the ideal generated by some irreducible polynomial. But that's something that you can prove. And that's something that we could have proven a long time ago, but we didn't. This is theorem 1.10 in these notes on finite fields by Keith Conrad. And you can show, even before you say anything about splitting fields at all, that every finite field of characteristic p is isomorphic to fp bracket x mod the ideal generated by some polynomial p of x that is irreducible in fp bracket x. So if you believe this theorem and you believe the theorem that we proved, then we have proven that for each p and n, there is at least one irreducible polynomial p of x in fp bracket x of degree n. But this is a very weird argument, because where is this irreducible polynomial of degree n? Like, where is it? And there's a nice answer to this question, which is this polynomial, x to the p to the n minus x. We showed that it was separable, but we didn't talk at all about factoring it. So this is something I'll come back to a little bit later. Section 14.3 of Dumb and Foot is all about finite fields, and proposition 18 tells you how to factor this polynomial. X to the p to the n minus x in fp bracket x. This is the polynomial of all distinct irreducible polynomials in fp bracket x of degree d, where d runs through all the divisors of n. Okay, so like if n is 4, this is the product of all the distinct irreducible linear polynomials times all the distinct irreducible quadratic polynomials. I guess I should say monic here. And then all the distinct irreducible monic quartic polynomials also. So from this proposition, you can count the contribution to the degree by the by each of these degrees d, how much of this degree p to the n comes from the polynomials of degree 1, degree 2, of degree 4, and so on. And there's a formula for the number of irreducible polynomials of degree d in fp bracket x. This is given on page 588 at the end of this section 14.3. And so we'll see by factoring this polynomial that there really is at least one irreducible polynomial p of x in fp bracket x of degree n for each n. So why are we not doing this now? Section 14.3 uses a little bit of what we're going to develop in the next several lectures about Galois theory applied to finite fields that gives a more streamlined presentation of some of this material. But if you want to get a head start, it would be totally reasonable to read through these finite fields by Conrad's notes by Conrad, which do not assume that you're already familiar with Galois theory.